Till now we have talked about convexity and concavity only for functions that are twice differentiable. Now we take up a more general definition that is valid even for functions that are not differentiable, and we are going to see in later chapters that it is going to be easy to extend this definition, the generalized definition, to functions of several variables also. So what we are going to take up now is this, that we have a function f, and this function f is called concave, and in brackets let me write convex, if the line segment joining any 2 points on the graph is never above the graph. And if I talk about convex function, so here if you have a line segment joining any 2 points on the graph, that line segment is never below the graph. Now if we take a look at these two diagrams, here we see that figure 9.27 shows a function which is convex. Figure 9.28 shows a function which is concave. If you get back to the definition that I have just written, f is called concave if the line segment joining any 2 points on the graph, so these are the 2 points on the graph, the line segment joining these 2 points is not above the graph. So it's a concave function. If I talk about a convex function, we say that the line segment, and there we see that the line segment joining any 2 points on the graph, that is never below the graph. Now we would now like to in fact give an algebraic formulation of this definition. This is too intuitive. We still have to formalize it, or in other words, we still have to give an algebraic formulation to this definition. For that, what we do is that let's take up an interval a to b, wherein a and b are inclusive, they are included in that interval, and we have a less than b. And let's say I take up any point in this interval. Now what I mean to say here is I just now take up any arbitrary point x in the interval a to b. I know that a is less than b. This point x can actually be written as x is equal to 1 minus lambda multiplied by a plus lambda b, or I can write a minus lambda a plus lambda b, which can then be written as a plus lambda b minus a. Now in this case, this is for some lambda belonging to 0 to 1. Why do I say this? Because let's say lambda is 0. If lambda is 0, that means x is if lambda is 0, then x is a. If lambda is 1, in that case if lambda is 1, then x is b. And if lambda lies between 0 and 1, then x will move between 0 and 1. As lambda goes from 0 to 1, then in that sense x, so I know that here lambda is equal to 0, x is equal to a, lambda is equal to 1, x is equal to b. That just means as lambda goes from 0 to 1, x goes from a to b. Now, given this, I obviously know that a is greater than b. No, not that. A is less than b. And if I just take up what I have written as x is this, a plus lambda multiplied by b minus a. Now if lambda is 0, then this expression is a. If this lambda is 1, then this expression is b. If lambda is between 0 to 1, this expression is between a and b. That means I can say that this expression is greater than equal to a. Why do I say equal to a? This is equal to a if lambda is 0. And I also know that this expression is less than equal to b, because the maximum value of lambda that I can have is 1, and if that is the case, then we have b. So that just means I can write a less than equal to a plus lambda, b minus a less than equal to b. On the other hand, if I start with x belonging to this, and now I put lambda equal to x minus a by b minus a. What is this? This is the ratio between, so x belongs to this interval. This is the ratio between the distance from x to a, that is x minus a, and the total distance from a to b, that is b minus a. So if you take a look at this expression, given the fact that x lies between a and b, so if x is a, this expression is 0. If x is b, this expression is 1. If x lies between a and b, this expression lies between 0 and 1. So I hope it's clear that first what we said was that we started with lambda being 0, we got x as a. If lambda is 1, we got x as b, and then we saw that a less than b implies a less than equal to a plus lambda multiplied by b minus a less than equal to b. Conversely, if I start with x belonging to a to b, that closed interval, and I put lambda equal to this, that just means this implies I have 0 less than equal to lambda less than equal to 1. And here what we see is that if we have this and 0 less than lambda less than equal to 1, then we have this. And we have now taken the other case also. So given all this, if I now write 1 minus lambda a plus lambda b, instead of lambda I just write 1 minus x minus a by b minus a plus lambda b, which is x minus a by b minus a multiplied by b. So that actually gives me b minus a and then a b minus a minus x plus a. Multiplied by a plus x minus a divided by b minus a multiplied by b. So this gives me minus a plus a, these get cancelled. So you have ab minus ax by b minus a. Then you have bx minus ab divided by b minus a. Earlier also it was ab minus ax divided by b minus a. Then it is bx minus ab divided by b minus a. So that gives us this. ab minus ax plus bx minus ab by b minus a. So what we have here is x b minus a by b minus a, and obviously I know that b minus a is not equal to 0. That just means this is equal to x. So that means we can easily see here that if I have this, if a is less than b and we have lambda belonging to 0 to 1 both inclusive, then we have this. Also we know that if x belongs to a to b and we put lambda equal to this, that just means lambda is lying between 0 and 1 both inclusive. So 1 minus lambda multiplied by a plus lambda b is nothing but x. Here what lambda is that here we have taken lambda to be the ratio between the distance from x to a and the total distance from a to b. So it actually is either 0 or 1 or somewhere in between. Now let's take up this diagram. Let's take up this diagram. Here we want to calculate the number s. We are given a function, and basically there is also a line that is going through, that is joining a f of a and b f of b. And if we are a little bit careful, we know that this line, we can actually go for that point formula of a straight line, and in this graph, in this diagram, we want to calculate the number s. For that, first we take up the line through a to, for that we first take up the line through a f of a and b f of b, and I know that this line has got the equation. So if you have x1 y1 and x2 y2, your formula would be y minus y1 is equal to the slope x minus x1, and you can easily calculate the slope. Slope is nothing but y2 minus y1 divided by x2 minus x1. So that's exactly what I do here. Let me write that equation. So let me write the line through a f of a and b f of b has the equation y minus f of a equal to f of b minus f of a divided by b minus a, and then x minus a. Again, we put x as 1 minus lambda a plus lambda b, and now let's see this. Why have I put x as this? Because of this, because here I see that I have the interval a to b, and x is, let us say here, it is 1 minus lambda a, it is 1 minus lambda multiplied by a plus lambda b. So this is by x, and now I would like to know what is this s. So this is the equation that I have. In this equation, what I now do is, so we have this equation with us. In this equation, we first put x as this, and corresponding to that we will get our y, and we know that corresponding to this x, and I consider that equation of that straight line which is joining a f of a and b f of b, the y will be nothing but s, as I can see from the diagram. Here, whatever we have, so if I have x is equal to 1 minus lambda multiplied by a plus lambda b, y is s, given the fact that I am considering the line which is joining a f of a and b f of b. So now what I do is, I put x as this in this equation, and then I will see what my y is, and that y will be nothing but s. So that means I have y minus f of a is equal to f of b minus f of a by b minus a, and then I write what my x is, because it is x minus a. So I just write 1 minus lambda a plus lambda b minus a. And now what I do is, I just go for f of b minus f of a divided by b minus a, and then I just see what I have here, a minus lambda a plus lambda b minus a. So that gives me this, that gives me f of b minus f of a by b minus a, and here I have lambda b minus a. So basically now I have y minus f of a equal to lambda f of b minus f of a, and that gives me, okay, now let's put y as s, and so let me write, we put y is equal to s, so s is equal to lambda f of b minus lambda f of a plus f of a. So s is equal to 1 minus lambda f of a plus lambda f of b. So I now have my s. Corresponding to my x, which is equal to 1 minus lambda a plus lambda b. So what we see here is that I already know that as lambda takes on all values in 0 to 1, it starts from 0, it goes on till 1. This number, this particular number, it takes on all values in a to b. So it starts with A as lambda is 0, and then as lambda goes upwards, this starts to increase. As lambda reaches 1, this becomes B. So this is something that I already am clear about, and that means I can just say that as lambda takes on all values in this, x will take on x, which is equal to this expression, or I can just write 1 minus lambda a plus lambda b. This expression takes on all values in this. Now, if I take up this diagram again, I know that here the function is concave. Basically, that means the line joining any 2 points on the graph of the function that is never above the graph, and that means the line joining these 2 points, let's say a f of a and b f of b, it should never be above the graph of the function. Okay, it should never be above the graph of the function. So that means it should always lie below the graph, or it should be on the graph of f. And that just means that if I take a look at this line, which is this, we know what s is, and corresponding to this expression 1 minus lambda a plus lambda b, this expression is f of 1 minus lambda a plus lambda b. So that means if my function is concave, this s just cannot be more than f of 1 minus lambda a plus lambda b, because I just said that when a function is concave, the line segment joining any 2 points on the graph of that function, that should never be above the graph of that function. Now, so here we can say that this is the line segment joining a f of a and b f of b. This line segment should not be above the graph of the function. That just means that if I take up this s has to be either equal to f of 1 minus lambda a plus lambda b, or it should be less than that. It should never be above, or it should never be greater than f of 1 minus lambda a plus lambda b for all lambda belonging to 0 to 1, both inclusive. So that just means we have this. Given that f is concave, that means the line segment joining a f of a and b f of b, this line segment should always lie below the graph of f. In fact, I should say below or on the graph of f, and that just means s should always be less than equal to f of 1 minus lambda a plus lambda b for all lambda belonging to 0 to 1. And that means I can now write what is s. S I know is equal to 1 minus lambda f of a plus lambda f of b. So this should be less than equal to f of 1 minus lambda a plus lambda b. All right, so that gives us the general definitions, and in fact that gives us an algebraic formulation of the general definition. So that means now I can write function f is concave in the interval I if for all a to b belonging to I and all lambda belonging to this, we have f of 1 minus lambda a plus lambda b greater than equal to 1 minus lambda f of a plus lambda f of b. Now this is when our function f is concave. Now I know that if minus f is concave, that means f is convex. So this is also something we have to keep in mind. That means if I want to think of what is the case when the function is convex, I just have to reverse this sign, and that means I can write function f is convex in the interval I if for all a to b belonging to I and all lambda belonging to 0 to 1, we have this f of 1 minus lambda a plus lambda b. This should be less than equal to 1 minus lambda f of a plus lambda f of b. And we can also think about it intuitively in both cases. Again, I'll repeat that when I say a function f is convex, that just means minus f is concave, so we just have to reverse the signs. And now if we take a look at these general definitions, it is going to become very clear that these definitions can even be applied to functions that are not even differentiable. And in fact, if we go for the first definition that I have written here about the function being concave, and obviously I know that a is less than b, a is not equal to b, and let's say we require this inequality to be strict. So let's say I have in this case greater than, just greater than, then my function f would be called strictly concave. If that is the case, that means f is strictly concave. And what it means is that if you join the line segment, and what it means is that if you have a line segment joining any 2 points on the graph of f is actually strictly above that line. Also, in fact, if I look at this diagram here, the graph is, as in the function here, is strictly concave, because what we see is that the graph of f is strictly above the line segment joining the 2 points on the graph. If you take a look at this figure 9.30, here we have a case wherein the function is concave, but it is not strictly concave, because if we take up these 2 points, and there is a line segment which joins these 2 points, the line segment lies on the graph of f. Okay, that's not the case here. Here the line segment, you take up any 2 points on the graph, you get a line segment that joins those 2 points. You see that the graph of f will always be strictly above that line segment, but that's not the case here in figure 9.30. So here the function is concave but not strictly concave. So that's clearly written here that the function is concave but not strictly concave. And if I talk about any function which is strictly convex, for that we can see this case, we can see this definition, and we just have to, again, if I say that f is strictly convex, that just means minus f is strictly concave. So that just means I would have to go for this, again a less than b, again a less than b, but this inequality will be strict in this case. So here I will say that f is strictly convex. Given all this, let's just take up a question. We have to prove that f of x equal to mod x, or the absolute value of x, is convex in minus infinity to infinity. Now let's just take a look at the graph of f.